All right, let's talk about one of the coolest, most powerful, and honestly most beautiful ideas in all of physics, Gauss's law. It's this incredible shortcut that lets us solve problems in electromagnetism that seem almost impossible, but with like a surprising amount of elegance. Okay, let's jump right in. So here's our game plan. We're going to start by seeing exactly why we even need a shortcut like Gauss's law. Then we'll build up this key idea called flux. After that, we'll unveil the law itself, see how to actually use it with symmetry, and finally, we'll connect it all back to how real-world materials, like conductors, behave. Okay, so why do we need this thing in the first place? Well, to really appreciate the genius of Gauss's law, you first have to understand the hard way of doing things, the brute force method, which you'll see gets really complicated really fast. Imagine you've got some charged object and you need to find its electric field. The textbook way is to, break that object up into a bajillion tiny little point charges and then add up the field from every single one. I'm talking about a million vector calculations, a ton of messy integrals. It's a total mathematical nightmare. There's just got to be a better way, right? And of course there is. The key, as it so often is in physics, is looking for symmetry. It turns out that for charge distributions that have a nice, simple shape, like a perfect sphere, a long straight line, or a giant flat plane, we can use a completely different approach that just sidesteps all that nasty integration. And that approach is Gauss's law. So, to unlock the power of Gauss's law, we first need to get our heads around this one crucial concept, flux. Now, it sounds a little abstract, I know, but the basic idea is actually super intuitive. Let's start with a simple analogy. Just picture a steady breeze of air flowing, and you hold up a little loop, like a hula hoop. The amount of air that's actually passing through that loop every second, well, that's a type of flux. We'd call it volume flux. The more air that goes through, the bigger the flux. Simple enough, right? Now here's where it gets interesting. It all depends on the angle. If you hold that loop perfectly face onto the wind, you catch the most air. That's maximum flux. But as you start to tilt it, less and less air can actually make it through the opening. And if you hold it completely edge-on, well, then zero air goes through. So to deal with this, physicists came up with a neat trick. They define the area of the loop as a vector, one that points straight out, perpendicular to the surface. The flux, then, is all about how well the airflow vector and that area vector line up. So let's make the switch. Instead of an airstream, we now have an electric field, which we draw as field lines. Electric flux, then, is pretty much the same idea. It's just a way of measuring how many of those electric field lines are piercing through a surface we care about. It's basically our way of counting the field that passes through a certain area. And to count them, we have the simple sign convention. We imagine some kind of closed bubble-like surface. This is what we'll call a Gaussian surface. If the electric field lines are pointing out of that bubble, we call that positive flux. If they're pointing in, we call it negative flux. And if a line just kind of skims the surface without going in or out, its contribution right there is zero. Now, to get the total flux for the entire closed bubble, we have to add up all those little contributions from every tiny patch of the surface. In calculus, we call this an integral, but really all we're doing is asking a simple question. On balance, are more field lines leaving the bubble than are entering it? Okay, so we've got this idea of flux. Now get ready for the moment where it all clicks into place. This is where the genius of Carl Friedrich Gauss comes in, connecting this idea of field lines piercing a surface directly to the source of the field itself, the electric charge. And here it is. Just look at how simple and beautiful that is. This equation is saying that the total electric flux, that's the capital Phi, passing through any closed surface you can imagine, multiplied by this fundamental constant of nature, epsilon naught, is exactly equal to the net amount of charge you've enclosed inside that surface, Q enclosed. That's it. The shape of the field is directly locked to the charge inside. Now this right here is the absolute key to the whole thing. It's the magic trick. Only the charge that's inside your imaginary bubble matters. Look at those charges on the outside. Sure, they make field lines, but any field line from an outside charge that enters the bubble, well, it has to exit it somewhere else. The inward flux and the outward flux from that external charge perfectly cancel out. Their net effect on the flux is always zero. Let's just trace this out on the diagram to make it crystal clear. Surface S1 wraps around a positive charge, and you see all the field lines pointing out, so positive flux. Surface S2 wraps around a negative charge, and the lines all point in, negative flux. Surface S3 has nothing inside, and you can see every line that goes in also comes out, so the net flux is zero. And surface S4, which encloses both, has a net charge of zero, and yep, zero net flux. It just works beautifully. So we have this amazing law. But how does it actually help us avoid those horrible integrals we were talking about earlier? Well, this is the payoff. This is where a little bit of strategy and a lot of symmetry turns a really hard problem into a surprisingly easy one. Here's the playbook. First, you just look at your setup of charges. What's its shape? Is it a sphere, a long line, a flat plane? Second, you strategically choose an imaginary Gaussian surface that has the exact same symmetry. This is the big brain move. Third, that symmetry makes the electric field super simple. It'll be constant everywhere on your surface. That turns a nasty integral into just simple multiplication. Finally, you set that simple flux equal to the enclosed charge and solve for the E field. Let's test it out on the most basic case we know, a single point charge. The charge has perfect spherical symmetry, so what do? We draw a spherical Gaussian surface around it. Because of the symmetry, we know the electric field has to point straight out and have the same strength, E, everywhere on our sphere. So the flux is just E times the surface area of the sphere, 4 pi r squared. We plug that into Gauss's law, do about 5 seconds of algebra, and boom, out pops Coulomb's law. It's not magic, it's just really, really good physics. Okay, let's try a different symmetry. How about a long, uniformly charged wire? Well, that has cylindrical symmetry. So we're going to pick a cylindrical Gaussian surface. Now, the electric field points radially out from the wire, right? Which means the field lines are parallel to the top and bottom caps of our cylinder. They just skim right past, which means the flux through the caps is zero. All of the flux, the entire thing, comes out through the curved side, where E is constant. The calculation becomes almost trivial. And for our last example, let's take a huge flat sheet of charge. This has planar symmetry. The perfect tool for this job is a small, cylindrical pillbox that pokes through the sheet. Here, the electric field points straight away from the sheet, so this time there's no flux through the curved sides of the pillbox. All the flux goes through the two flat end caps. And this leads to a pretty wild conclusion. The electric field from an infinite sheet of charge is constant everywhere. That's right, it doesn't get any weaker as you move away. All right, for our final piece, let's apply this incredibly powerful law to something tangible, something from the real world, an electrical conductor, like any piece of metal. So here is a fundamental truth about conductors, one that we can now finally prove. If you take a chunk of metal and you dump some extra charge onto it, that charge doesn't just sit around inside. Nope. It all rushes to the outer surface. But why? Gauss's law gives us this just beautifully simple proof. We know that once things settle down, what we call electrostatic equilibrium, the electric field inside the metal has to be zero. If it wasn't, charges would still be moving around. So let's draw a Gaussian surface just barely inside the physical surface of the conductor. Since E is zero everywhere along our imaginary surface, the total flux through it has to be zero. And what does Gauss's law say? If the flux is zero, the net enclosed charge must be zero. This forces all that excess charge to be outside our Gaussian surface, which means it has to be on the actual physical surface of the conductor. It's so elegant. And this has a really fascinating consequence. The electric field right outside a charged conductor is actually twice as strong as the field from a non-conducting sheet that has the same amount of charge spread over its surface. That factor of 2 is there because with a conductor, all the charges work together to create a field pointing only outwards, basically concentrating all their firepower in one direction. In the end, Gauss's law is so much more than just a tool for calculations. It's a really profound statement about the deep connection between sources and their fields, all seen through the beautiful lens of symmetry. It shows us that by looking for patterns, by looking for simplicity, we can unlock a much deeper understanding of how the universe actually works. And it makes you wonder, right? Where else are these elegant shortcuts just waiting for us to find them?